Question 17. In a particular electrical circuit, the voltage V, volts, across a capacitor is given by V of t equals 6.5 times 1 minus e to the power of negative kt in brackets, where k is a positive constant and t is the number of seconds after the circuit is switched on. Part A. Draw a sketch of the graph of V of t showing its behaviour as t increases. Let t equal 0 to find the initial voltage on the capacitor, and that will be our starting point when drawing the graph. So the value of V of 0, which represents our initial voltage, is equal to 6.5 times 1 minus e to the power of 0 in brackets. Now e to the power of 0 is equal to 1, and 1 minus 1 is equal to 0, and 6.5 times 0 is equal to 0. So V of 0 is equal to 0, and that represents the starting point of our graph. Let's see what happens as t approaches infinity. In other words, as time gets larger and larger, or as we progress further and further in time, let's see what happens to e to the power of negative kt. Now k is positive, so we have a negative here, so a negative positive, which makes a negative, multiplied by a large value of t. Effectively, what we're doing is e to the power of negative infinity. So as t gets bigger and bigger, e to the power of negative kt gets smaller and smaller, in the sense that it gets closer and closer to 0. So if we think about it in terms of limits, the limit as t approaches infinity of e to the power of negative kt is equal to 0. Hence, v of t approaches 6.5 as t approaches infinity, because this e to the power of negative kt approaches 0, which is this term here, and then we're just left with the 1. So 6.5 times 1 is just 6.5, and that's why v of t approaches 6.5 as t approaches infinity. And that is in fact our horizontal asymptote on the graph. Now it's a negative exponential graph in the sense that it rises more rapidly in the beginning, but then it shallows out, and the gradient of the tangent on this curve approaches 0 as we get closer and closer to the horizontal asymptote. So here's the graph, here's our origin, there's the horizontal axis, which is time, our vertical axis, which is voltage, V of t, and the horizontal asymptote needs to be clearly marked at 6.5, and the curve should approach the asymptote but never touch it, as so. Part B. When t equals 1, the voltage across the capacitor is 2.6 volts. Find the value of k, correct to 3 decimal places. We are given that V of 1 is equal to 2.6. In other words, when t equals 1, the voltage across the capacitor is 2.6 volts. Hence, we can form the equation 2.6 is equal to 6.5 times 1 minus e to the power of negative k times 1 in brackets. Now, negative k times 1 is negative k, and we can divide 2.6 by 6.5 and we get 0.4. So the equation simplifies to 0.4 equals 1 minus e to the power of negative k. Subtracting 1 from 0.4, we get negative 0.6 is equal to negative e to the power of negative k, and we can rewrite that as e to the power of negative k equals 0.6. Since we have a negative here and a negative there, if we divide by negative 1, the 0.6 here becomes a positive, and the e to the power of negative k also becomes a positive. Now we have base e here, we want to solve for k, so we can take the natural logarithm of both sides of the equation. So we get ln of e to the power of negative k is equal to ln of 0.6. So simplifying the left-hand side, we get negative k, and that's equal to ln of 0.6. Dividing both sides of the equation by negative 1, so we can isolate the k, we get k is equal to negative ln of 0.6, which evaluates to 0.5108256 and so on. But the question is asking for the value of k correct to 3 decimal places. Therefore, k is equal to 0.511 correct to 3 decimal places. Part C. Find the rate at which the voltage is increasing when t equals 2, correct to 3 decimal places. Part C is asking for an instantaneous rate of change of voltage with respect to time. So we will need to differentiate the voltage equation V of t equals 6.5 times 1 minus e to the power of negative kt in brackets with respect to t. To make the differentiation a little easier, we can expand the brackets first. So V of t is equal to 6.5 minus 6.5 e to the power of negative kt. Now we can differentiate V of t with respect to t. Now the derivative of a constant, so in this case 6.5, is 0. So we only have to differentiate negative 6.5 e to the power of negative kt. So applying the chain rule, v dash of t, which represents our first derivative, is equal to negative 6.5 times e to the power of negative kt times the derivative of the index with respect to time, or with respect to t. So we're multiplying that by negative k. And that simplifies to 6.5 times k times e to the power of negative kt, where k is equal to 0.511, which we found in part A. So to find the rate of change of voltage across the capacitor at the 2-second mark, we substitute 2 for t in the first derivative here. So v dash of 2 is equal to 6.5 times 0.511 times e to the power of negative 0.511 times 2, which evaluates to 1.195323 and so on. Now the question is asking for the rate of change correct to 3 decimal places. So this rounds to 1.195. Therefore the voltage is increasing at the rate of 1.195 volts per second at time t equals 2.